Welcome to UV Physics Academy. So here in the last class we have discussed about this bit flip error, and today we are discussing about this phase flip error. Okay, correction. So but here the small issue is we don't have any classical analogy for this. No classical analogy. Then the question is how to do this correction. But there is a possibility we can convert a phase flip model. So we can convert a phase flip model to bit flip model, which we have already discussed in the earlier class. So by transforming the basis. So what are these bases and how to transform? So just transforming from a z basis. Z basis means get 0, 1, to the diagonal basis, that is a plus and minus. So these are the z basis, and here we can say these are x basis or diagonal basis. This can be done by using the Hadamard gate. So Hadamard gate can convert, I mean, z basis to diagonal basis and vice versa. Okay, fine. Okay, so main idea is phase flip model, how to detect this phase flip. So we are converting the phase flip model to bit flip model by transforming the basis from z basis to x basis. I hope you got it. Okay, so the first step, let us take, I mean, if you want we can take like this. H operates on 0, we get 1 by root 2, so that is a 0 plus 1, so this is nothing but plus. And similarly h operates on 1, so this is a 1 over root 2, so 0 minus 1, which is nothing but minus. Now let us take the encoded circuit. So first I am taking earlier whatever we have taken for bit flip, the same thing I am taking. So this is the psi alpha 0 plus beta 1, and here we have get 0, sorry, 0, and this is 0 qubit. Now this is entanglement C naught, and here also C naught. Then we got earlier in the last class alpha 0 0. I mean, here if you take this one, so it is alpha 0 0 0 plus a beta 1 1 1. So in the bit flip model we got like this. Now we want to convert into a phase flip model. That's why we are adding one Hadamard gate to this. So one, I mean, so we are taking the 3 Hadamard gates here, H and H and H. So once the Hadamard gate operates on this, we'll get alpha plus 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 beta minus minus minus. Okay, so the Z bases are transformed to X basis with the help of Hadamard gates. Okay, fine. So now let us suppose there exists some noise. Okay, so here we are talking about this decoherence or noise. Okay, so this is, let us say I tensor I like this, and the next one, sorry, so here it is Z I I I Z I identity, and here it is Z. So we can say the first one, there is a no error, and here we have, this is the Z gate. Okay, so here we can say that there is a first qubit is having a phase flip, and here the second qubit is having a phase flip, and here the third qubit is having a phase flip. Okay, so this is the encoded circuit. Now the next step, so I told you in the last class 3 steps. First one is a transformation. So the transformation is done. And the second one is, second one is a syndrome detection. So let us discuss the syndrome detection. Right. So now let us go to the next step, that is a syndrome detection. Okay. So I told you, first I will take the bit flip model only, and after that I will convert into phase flip. So in the last class, if you see, we have taken the bit flip model like this, and here we have three qubits x1, x2, x3, and here we have two ancilla bits. Those are 0, 0 here. Right. Now we have taken the C naught gate, and from the second, and next from second to here, and from third, right? And after that we have taken this is, these are s1, s2 something. Okay, so this is bit flip syndrome detection circuit. Now if you carefully observe, so here if you see this noise here, okay, we can write like this also. After this it becomes alpha plus plus plus, so because there is no correction, minus, and here first bit means alpha minus plus 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 a beta plus plus, sorry, plus minus minus, and here the second bit, that is plus minus plus, and a beta minus plus minus, and here alpha plus plus minus plus beta minus minus plus something like this. So what I want to say is here we are in a diagonal basis. Okay, so here we are in this diagonal basis, but if the circuit is the bit flip model, so we need Z basis. So for that I'm going to add one head gate here, and for x2 also, and for x3 also. Then what happened, and here we got a Z basis. Okay, so again it converted to a 0, 0, 0 and 1. So these are the Z bases. Now after that, if you see carefully, and this one, this circuit, this circuit, so this is the same as a bit flip model. Okay, now after that, here we have S1 and S2. In the last class I have discussed already, S1 is nothing but x1 XR x2, and S2 is nothing but x2 XR x3. Fine. So once you make a measurement, okay, so once you make a measurement, so we'll get either 0 0 or 0 1 1 0 1 1. Okay, so but again we need again that diagonal basis. For that, here we have to add three more Hadamard gates like this. Okay, so then again it is converted into diagonal basis or x basis. So this is the syndrome detection. Now let us discuss what are these S1, S2. Right. So now let us check how we are getting that S1, S2 values. Okay. So please observe, we converted the bit flip model into phase flip model by using this Hadamard gates. Okay. Right. Now here, initially we have this one here. So diagonal basis, here diagonal basis. So here I'm taking plus plus like this. Right. So these are x basis. Now once you apply this Hadamard operation, that is h tensor h tensor h, So this converted into z basis 0 0, like this. Right. Okay. So now by using this, earlier already we have explained in the bit flip model. So S1 is nothing but X1 XR X2. That means, for example, if you have this XR gate, so let us say this is X1 and X2, this output is X1 XR X2. So what is this XR gate? That is the inequality finder. Inequality, inequality finder. So that means wherever, I mean, if inputs are unequal, then the output equal to 1. So that's it. Okay. So now please focus on this x1 and x2. If you see this here, so both are same here, here both are same. So that's why you will get 0 0. And after that here both are different. So that's why you'll get 1 1. And again different 1 1. Next again same 0 0. And S2, if you want to check, then you have to see these two, that means here. Okay, so by using that we get here a 0, next a different different, same same, different different, the same. And again we will convert this into a x basis. So again it will be transformed to a diagonal basis. Right. So like this we will get the S1 S2 values in the syndrome detection circuit. So for example, if you represent this in another format, here S1 S2 0 0 and 0 1 1 0 and 1 1. So if you see this 0 0 here, we have this no change. That means plus 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 and here minus. And the next one 0 1. If you see this 0 1 here corresponding to this, we have third bit flip, sorry, third phase flip, that is plus plus minus 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 plus, here third one. And if you see this 1 0 here in the middle, okay, so corresponding to this, here we have the first flip, that is minus plus 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 minus minus. And the last one, if you see this 1 1, here these two 1 1, and second flip, that is plus minus plus minus plus minus, like this. So here is the second one and here is the first and third. Like this we can represent. Now the syndrome detection is completed. Now let us discuss about the stabilizers. Okay, so let us see what are the stabilizers here. So in the last class I told you stabilizers means these are Hermitian operators whose square equal to I with the eigenvalues of plus or minus 1. So in the bit flip model we have stabilizers Z1 Z2 because the Z operator acts like a parity operator, parity checker for that Z basis. And here that duty is done by, or that function is done by X gate, Pauli X gate. So that's why here the stabilizers are x1 x2 and x2 x3. So that means, for example, x1 x2, and I told you already these stabilizers commutes, so that's why they have common eigenstates. X1 x2 operates on psi, maybe plus or minus a psi. This is a syndrome state. And similarly x2 x3 operates on psi, will get plus or minus psi. Okay, so now, so here I have taken that earlier S1 S2 table. So now let us say these boxes, this first one, second, third, fourth, these are syndrome states. Now I told you corresponding to S2 we have X2 X3, and corresponding to S1 we have X1 X2 stabilizer. So we can say like this, x1 s2 operates on psi, we get minus 1 whole power s1 psi, and x2 s3 operates on psi, this corresponds to minus 1 whole power s2 psi. Now let us check. Now for example, if I take this one here, if you take the first one, we'll get, sorry, x1 x2 plus x1 x2. Wait a minute. So if you see here, x1 x2 operates on plus plus, similarly x1 x2 operates on minus minus. Okay, so here we are having a plus eigenvalue, that means parity, no parity change. And similarly, if you take the means here it is a plus, here it is minus, here it is plus, here it is minus, because this is a minus 1 whole power s2, and here minus 1 whole power s1. In the earlier class also we have discussed. Now for example, if you take some other one, this one let us take. Okay, let us check. x1 x2 operates on plus minus plus, so here it is plus only, and once this x2 operates on this minus, we'll get minus of, like this. That means earlier z operates on 1, we'll get minus 1, and here x operates on minus state, we'll get minus minus. Similarly, if you take x2 x3 operates on plus minus plus, so here also x2 is operating on this minus state, so that's why minus again, we'll get plus minus plus. Like this we can check the parity checking by using this stabilizer operators. The next one is a correction. So how to do this correction? Right. So I have taken again the circuit. Okay. So syndrome detection circuit I have taken. Now correction. So earlier we have already discussed. Now for example, if you see here 0 0, so nothing to do. That means no error, no need to do anything, leave it. At the next one, here S1 S2 0 1. So come to this 0 1. So which bit is having a phase flip? The third one. Okay. So here, oh, okay. So here we have to take a anti-control as usual, and here it is a control. In the last one, bit flip model, we have taken X. Okay. So here we are taking a Z. That's it. So third one, like this. Okay. And the next one, 1 0. If you see 1 0 here, so first bit is having flip, so that's why here this is a anti-control and this is a control, and after that the first one is having a Z, right? And the next one 1 1, if you see here 1 1, the second bit is having a flip, so here it is control, and this is also control, and the second one is having a Z gate, like this. So with this we can correct the phase flip error. Now let us see the simulator. Okay, fine. So I hope you understand. After this again this will become, if you see here, it will become alpha plus 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 as beta minus minus. So initial state. Okay. Now let us discuss and let us see in the simulator how it works. So this is yesterday bit flip circuit. Okay. So bit flip errors detection and correction circuit. Now just I am converting this into phase flip by adding this head mod gates. Okay. And again here also head mod gates, like this. And one more thing, we have to replace this X gate with Z, sorry, here, and this Z gate with this one, like this. Now please check. And here we should take a diagonal basis plus. Now let us suppose the middle one is having a error. That means minus. Now see carefully, if it is minus, okay, so here we have S1 S2 1 minus, 1 minute, yeah, sorry. So here it is a plus, and the second one, please observe, minus, and the third one is plus. If the second bit is having a flip, phase flip, minus, then here we are getting S1 and S2 1 1. Okay, I hope you are seeing. Okay, now if you observe carefully again, once you operate, I mean, once you do this, once you take this correction circuit, here we are getting again, there is no phase flip. If you want to see, please check here, there is no phase flip, okay, here. Or if you remove this, for example, correction circuit, if you remove, then maybe you may understand. Wait a minute. So now check here, here the middle one is having a flip, phase flip. Now if I correct this, because S1 S2 1 1, then I have to take both controls, and the middle one Z. Now see, there is no phase flip. Okay, so like this. Okay, I hope you understand how we have converted that bit flip model to phase flip model. So if you have any doubt, so please contact. Okay, so thank you, and we'll meet in the next lecture.